So here is problem number 4. And so this problem is a series parallel sort of problem here. But what they're giving us is the loads. So they're giving us these loads here. And they're telling us, up here they're telling us that this is an inductor. And they're telling us that this is a capacitor. Okay. And so there's a capacitor there. But there's also wattage here. So up here they gave us there's 0 watts. But down here we have 100 watts. And down here we have 0 VARs. But we have 300 watts. So what are they really saying? What does this circuit look like? Well, if I can try to sketch this out here. Guess I'll shrink it back a little bit so I can draw down below it and keep it all on the screen. All right, so what they are saying is that here's my voltage, and they're saying there's an inductor here. Okay, and so this is load 1. And then here, they're saying I've got a capacitor and I have a resistor. Okay. And so this is load 2. And then this over here is just a resistor. Okay. So that is what they are telling us in this problem here. So again, this is page 901, I think, in the book. Figure 2051. Yeah, page 901. All right. And so what they're doing is they're telling us how much apparent power is in each load. Okay. And so then so they're going to ask us to draw the power triangle and find the total current and various different things like that. Okay. So this is just, they have several examples in here. All right. So to find this, remember, we need to go back. Of course, I erased those equations, so I'll have to rewrite them here. All right, so we had a couple of different equations here. All right, we had that S is equal to VI conjugate, which is equal to P plus, technically there's the JQ here if you're remember, P is always an angle 0, and Q is always an angle of either a plus or minus J, depending on whether it's a capacitor or an inductor. All right. But also remember what I talked about near the beginning of class. We had that the total power P, so we had like P total is equal to each one of these powers. Okay, and so the same thing with apparent power. Okay, with apparent power, you have the total apparent power is the sum of all your powers. So if you look here, they're telling us these, you know, over here's load 1, right? So they're saying that's S1. And this is S2. I don't know if you guys can hear that, but my dog's in here snoring. And this is S3. It's not me. I didn't fall asleep. I'm not talking in my sleep. Okay. All right. So, but these are the powers, but they're just giving us the load. So they're apparent powers. Okay. Thanks, Dan. All right. So these are apparent powers. And so these apparent powers are just going to add up. It doesn't matter whether they were in series or parallel. Okay, it will affect your currents depending on how they're hooked up. The current would be affected, absolutely, but the powers is just, this is how much power we're using. Okay, and so you just add those together. But remember, there is J's in here. So there, if there's an inductor piece, okay, so if there is an inductor piece here, that's a positive J. And if there's a capacitive piece, that's a negative J. So we got to, when you're adding this, you got to remember that technically there are J's. There's that imaginary portion for the Q over here. So we have to remember, right, that the Q part has a J plus or minus J. Actually, let me just even add a plus minus there. So it's plus or minus J, depending on whether it's a capacitor or an inductor. And the reason, if we go back to this conjugate piece, the reason we use that is because when you're talking about P and Q and you're talking about the J, if it's a capacitor, it's still a minus J. Okay, and if it's a inductor, it's still a positive J, and that's why they kind of play this trick, if you will, with the conjugate piece here, is to keep it consistent. All right, so what we need to do then to find the total current, right? We're basically looking at this equation. So voltage times the current gives us the apparent power. And they give us the S1, the S2, the S3. Okay. All right, so we just basically have to come in then and add those together. So if we just come over here, we're going to have S1. S1 was given as 0 plus a J 200. And S2 is given as 100 minus J 600. And S3 is given as 300 plus J0. And spread them out a little bit there and make it a little easier to read. All right, so now then S total is equal to 400 minus J 400. Isn't that convenient? All right. And so this, remember the units for this is vars. By the way, if we're putting this in Blackboard, we're going to need our decimal points, okay, for our 3 significant digits, and the units for this would be volt amperes. And I'll just make this a sub. So apparent power total is right there. And so hopefully you guys can kind of look at that and see that's a minus 45-degree angle. All right. And so then coming back up here to our original equation then, all right, we have that S is equal to V times I conjugate, okay, which gives me, all right, so if we rearrange this then, we're looking at I conjugate is equal to S divided by V, right? And I guess the other crazy thing there is if you look at this problem, what they like to do in this book, they gave us this to be a minus 90 degrees. Okay, so they gave us up here S, or E, I mean, to actually have a minus 90 degrees, which I usually reset those back to 0. But so he gave us E originally up here as having this 90-degree phase shift. Okay, so in that case, I conjugate is going to be 400 minus J 400 divided by 100 angle positive 90 degrees. Okay, so if we leave that in there, all right, so (400) minus J times 400 divided by, and you need to make sure that you are using parentheses correctly in your calculator, whether it's Octave or one of your TI calculators or whatever. Make sure you use parentheses here. To calculate this. Okay, so I'm just calculating this. Somebody got this yet? 5.66 at an angle of minus 45. Okay. I'll just double check it. Yep, that's what I got also. Okay. Okay, so, and that, but now remember, this is the conjugate. So I wrote that out there so we could see there, right? This is the complex conjugate. So what is my current? Okay. So actually, so what is the current then? Well, the current, I, becomes, 5.66 amperes at an angle of positive 135 degrees. Okay. So you got to be very, very careful now when if I ask you what is the current, okay, well, this equation was using the conjugate. So whatever your angle came up to be, when I ask for the angle of the current, you better remember the current I is not the conjugate, so you got to flip that angle. All right, so now given this though, we can go through and we can calculate the, we know, for instance, like this is the total current we calculated, all right? So that's the total current. So the current through load 1, is that current that we just calculated. And so therefore, we can calculate what is the reactance of load 1. So we can say load 1, okay, has an inductive reactance. We know it's inductive reactance because they told us that, so there's no doubt that is the inductive reactance there. And so that current, okay, so we have Q. They gave us, this was the load, and the Q portion of the load was the 200 VARs. Okay, so, all right, the Q portion of this is the 200 VARs. Okay, and so as we kind of talked before, I don't know if I kind of gave you this, but we had like power is equal to V times I times the cosine of the phase angle, okay? Or you can always look at it as I times R, right, which is Ohm's law, which gives you I squared R. Okay, that's I squared there. Okay, well, you can say the exact same thing for Q. Okay, so Q Q is equal to V times I times the sine. All right, but we know that the sine here, the voltage, this is just an inductor, okay? And so the voltage, there's a 90-degree phase angle here. So the cosine, I didn't put that up there. That was the cosine of 0. Okay, and the reason that's the cosine of 0, the reason this is the cosine of 0 is because if you're only looking at a resistance, okay, for a resistance, the voltage and current are in phase, which means 0 degrees. Okay, and so when we talk about a reactance, the voltage and the current are 90 degrees out of phase. Okay, and so the sine of 90, which is equal to the sine of minus 90, is equal to 1. And up here, the cosine of 0 is 1. All right, and so when we look at this Q then, right? So when we look at Q, we can say that Q is equal to I times our X of L, okay, or X of C if it's a capacitive piece, okay? There's X of L here. Okay, and so looking at that, I can now say, I can come back over here and I can say then that X of L, I started writing this, sorry, and I got sidetracked. So X of L is equal to your Q divided by I squared. Okay, and so we know the current. Okay, we know that in the inductor, they are 90 degrees out of phase. That's a known. Okay, and that's why I can say this. Okay, so we're not worried about this phase angle. We just know that this is the current with this phase angle. Okay, but the voltage is 90 degrees out of phase with this current, whatever the phase angle of that is. So we can, you know, the voltage is actually 90 degrees ahead of that. So we would add 90 degrees. Okay, and actually, I'm sorry, I was pointing at the wrong one. This is actually my current. Okay, but so we can calculate X of L now. So X of L here okay, so X of L is equal to the magnitude of the current squared divided by Q, where Q was, what was Q there? 200, I think. Okay. All right, so when we look at this, I'm just going to do the one because we're pretty much out of time here. But the X of L, okay, 6.25 ohms. So, okay, so 200 divided by the 5. Yeah, 6.25 ohms. I concur with that, Austin. Okay. All right, so that is my X of L. And again, that's going to be ohms. Okay, because that's the reactance. And if I knew the frequency, I could calculate that. Okay. And then we can calculate the voltage. Let's just do that real quick. The voltage across this inductor, right, is the current through it times the Jx of L. Okay, so we have J times X of L times that current and then if we wanted to calculate I need to put that in polar form. Okay, what was my current? Okay. All right, so you guys got it ahead of me there. 35.2. All right, so we got some differences here. Okay, so it's a 90-degree phase angle. So your phase angle needs to you need to, let's see, and it's a positive phase angle. So 135 gives me 225, or if we shift that, okay. Yeah, so V polar, yeah. So I'm getting a minus 135. Okay, yeah, I get a minus 135 also. Let me put that in here. So all right, so here's my calculation. Okay, so I had to calculate the current. So remember, the current was a positive angle. Okay, so the current had a positive J piece. But it was a negative here, so it's minus 180, and then that 45, so that was a positive 135 for the current angle. And so this gives me my current in rectangular form. And then I multiply that times J times the X of L value, which we calculated right up here. Okay, and so then that gives me my VL here. And then if we convert into polar form, it becomes a negative 135. So now notice here, okay, you know, it's what you're doing is you're looking at this is your current. Okay, it's these phase angles get a little confusing here sometimes because this is minus 135 degrees, or it was, excuse me, the current was plus 135 degrees. But if you think about your plot like this, okay, minus 135 degrees. Let me see if I can draw this right. So this current is going out here. This was our current going out here, and this was the angle plus 135 degrees. And now we have the voltage, which is going this way, which is minus 135 degrees. And this here angle, it doesn't look very much like it, but this is your 90 degree angle here. Okay, because remember that your 90 degrees, right? So your reactance gives that the voltage is 90 degrees out of phase with the current. And so, you know, you're looking at your current up here that had this plus 135, and you're looking at the voltage and it's a minus 135, and you're like, well, wait a minute, I thought there was a 90 degree phase shift. Well, this is the 90 degree phase shift piece right here. Okay. And that's why, okay, X of L is not at 0 degrees, X of L is at 90 degrees. Okay, so there's the current and the voltage are 90 degrees out of phase in an inductor. Okay, and then you could go through and you could calculate the voltage. Now that we have the voltage, that was the voltage across this piece right here in this circuit. So we could then calculate the voltage here, which of course these two are in parallel, so it's the same voltage. And then we could then determine, well, what is the current through S1 and what is the current through S3, or excuse me, S2 and S3. And of course, you know, I'll be putting a homework out there for you. So you guys can work through one of